the specific heat of solids, and the solids that we are going to focus on are the insulating crystals, and I'll tell you in a minute why insulating crystals. But before that, let's try to recapitulate what we learned over the last two lectures and a bit of some new stuff. So, we will learn this by means of filling up this table. Okay? So, first I take 1D with 1 atom per unit cell. So, it is really the monoatomic chain per. So, I am going to write P dot U dot C to mean per unit cell or per basis point. So, what is the Brillouin zone? Size of Brillouin zone. So, let us say in each case, in all these crystals that I am going to note down here, in all cases the number of lattice points is fixed. So, let me just make this as a note that in all these cases the number of lattice points is n. So, it is a n point lattice. Lattice points is capital N in each case. So, here you have n, and the spacing between the lattice points is A. Okay. So, here also the spacing between the lattice points is A. So, here is your 1D Bravais lattice, and the lattice points are spaced at a distance A with respect to each other. So, what is the Brillouin zone? The Brillouin zone extends from where to where? Minus pi by A to plus pi by A. So, that is the size of the Brillouin zone. So, you say minus pi by A to plus pi by A. Okay. How many k points are there inside this, in this space, in this range from minus pi by A to plus pi by A? How many k points are there? Today you should be able to answer this question. Number of k points is n. Number of normal modes is n. Number of k points is n. How closely spaced are they? What is the spacing between any two k points? We are going to call that as delta k. So, how much is delta k? Delta k is 2 pi over A capital N. That is how small the spacing is. Remember, n is a large number. How many normal modes exist? N, because we have n atoms and oscillators, and we are living in the 1D world. So, they can only move back and forth 1 degree of freedom per atom, n atoms, n degrees of freedom, n modes. So, therefore, a total of n modes. How many branches? Only one. How many acoustic? How many optical? One acoustic, no optical. Good. Let us move to a slightly difficult case, which is 1D with 2 atoms per unit cell. So, 1D but with 2 atoms per unit cell. So, the underlying Bravais lattice has not changed, but at each lattice site you are putting a basis of 2 atoms, 2 atoms PUC. What is the size of Brillouin zone? It is the same, minus pi by A to plus pi by A. How many modes? How many k points? It is the same. Number of k points is n. What is the spacing between the k points? It is the same. How many normal modes? 2n. 2n. Number of normal modes are 2n. Why 2n? Can you give a justification for 2n? So, yes. So, to locate the center of mass of this oscillator, this basis, right, you need one coordinate, which is x, because you are living in 1D world, and then there is this the stretching mode which is there, right. So, in principle you have 2 degrees of freedom, or you can say since there are n atoms, you have 2n degrees of freedom, and therefore you have 2n modes, and you know that these 2n modes are distributed over 2 branches, right. So, the number of k points have not changed. What has changed it is that for each k value you have 2 omega values corresponding to the 2 branches, right. So, you have 2 branches, and one of them is acoustic and one is optical, right. Now, let us advance to a case where we have 2D, but with 1 atom per unit cell or 1 atom per basis point. Okay. So, now you are in 2 dimensions, all right. So, since you are in 2 dimensions, so your lattice is going to look like this. So, the spacing between the lattice points is A. So, I am going to, for convenience sake, I would say that the spacing along the x axis is A subscript x, and the spacing along the y axis of my lattice is A subscript y, where Ax is equal to Ay is equal to A. Well, it is not necessary that they should be equal, but just I am taking a square lattice to demonstrate the point. So, here you have how many lattice points? The number of lattice points are still the same. So, you have nx lattice points along the x axis and n subscript y lattice points along the y axis. So, the total number of lattice points is like now a grid. So, the total number of lattice points, which is n, is equal to the number of lattice points along the x axis times the number of lattice points along the y axis, right. And nx and ny, because Ax is equal to Ay. So, therefore, nx is equal to ny, and this is equal to square root of n, right, any of these, right. And the dimension, the length of the lattice along the y axis will be how much? Will be Ay times ny, and along the x axis Ay times Ax times nx, right. So, these are simple thing. Now, here you have an atom. Now, this atom has how many degrees of freedom? How many degrees of freedom does this atom have? This atom has 2 degrees of freedom, right. I mean, it can displace along x axis or it can be displaced along y axis, and any general displacement can be written as a superposition of these 2 displacements, right. So, it has 2 degrees of freedom. So, therefore, okay, we will come to that in a minute. We will first let us decide the size of the build one zone. So, what do you think is the size of the build one zone in this case? Look at the lattice, yeah. Very good. So, that is the build one zone. So, the first the build one zone will extend. So, this is how the build one zone is going to look like, right. This point is, the coordinates of this point are minus pi by a sub y, sorry, x, comma, minus pi a sub y, and the coordinates of this point are going to look like pi by a x, comma, pi by a y, right, and so forth for these two, right. And the central point here has the coordinates 0, 0, and this point is known as gamma point. So, gamma point is always the center of the build one zone. So, here is the build one zone in the case of 2D. You have seen it many times before, right. So, here is the build one zone. So, how many k points will be there? The number of k points is not going to change, because that is determined by the number of lattice points. So, the number of k points are still going to be n. Okay. And what about the spacing? The spacing between the k points. So, the k points are now inside this, like this, and because n is very large, so the number of k points are also very large, isn't it? And if you zoom in any part of this, if you zoom in this region, for instance, what would you see? If you zoom in this region, you would see inside, you would see the k points nicely lined up, making a square lattice. This is this, like this. And what is the spacing between them? The spacing between them is as before, which is 2 pi by a n x along the x axis and a n y along the y axis. So, along the y axis it will be 2 pi by a sub y n y, and along the x axis the spacing between any two k points would be 2 pi by a x n x. Okay. So, remember, I mean, this is the important point. This is where the students get confused. Why this number is not changing? So, you have to come to terms with this. Okay? Yeah. I mean, try to argue yourself that the number of k points would still be k. The number of modes have changed, of course. Okay. So, now in this case, the plotting the dispersion is a little bit tricky, because okay, you have the kx, this axis is kx and this axis is ky. So, you can take an axis which is out of the plane of the board as the omega axis, then omega versus k will be a surface, right? Omega versus k will be a surface. So, more often than not, what you do is you do not show this surface, but you show the dispersion along specific directions. So, this point is typically this corner point, we can call this point as x, and this point can be labeled as m. So, I may be interested in the dispersion along the gamma m line or the dispersion along the gamma x line, which essentially means taking a section of the surface, right, omega kx ky surface along this direction or along this direction or maybe along this direction. People show all these things. So, we have discussed the spacing here. Now, what about the number of modes? How many modes should be there? We just discussed that each atom has 2 degrees of freedom. Total atoms are n. So, therefore, 2n. So, the number of normal modes are going to be 2n. Okay? So, the number of normal modes are going to be 2n. How many branches? 2, because the k points are still the same, n, and you have to accommodate 2n modes. So, therefore, there better be 2 branches. Are they optical branches? No, they are only acoustic branches. So, there are 2 acoustic and 0 optical. So, what the dispersion would look like in this case? The dispersion, this is, let us say, the zone boundary, and let us say we are plotting along which direction you like the most, let us say along the kx. Suppose we are plotting along kx. So, this is kx. Now, you have to specify whether you are plotting along ky or kx, and then you will see 2 optical branches. Now, we go to our more complex case. I thought we will not have to erase it, but looks like we will have to. Suppose we are in 2D and we have 2 atoms per unit cell. So, this is case number 1, 2, 3 and now 4, and 4 is you are still in 2D, but you have 2 atoms per unit cell. What is going to happen now? Now, you see you have 2 atoms at each lattice point, right. So, so one thing is that you have now, how many degrees of freedom do you have? 4n degrees of freedom, right? Two translational as before, and then 2 orientational. So one is the stretching, and the other one is that in the xy plane this can be anywhere. Think of it as a diatomic molecule and lying on the xy plane. So in the xy plane it can go do like this, or it can do like this, isn't it? So therefore now how many modes, normal modes you will have? Number of k points will still be n. That's not going to change, but the number of normal modes will be 4n. Number of branches will be 4 because you have to accommodate, and now you will have 2 acoustic and 2 optical, right? So this should also be giving you an idea about the origin of the acoustic and the optical branches. The optical branches comes only when there is a basis. The optical branches come only when there is a relative motion between the basis atoms, right? So the optical branches comes by virtue of having the basis, having a basis of polyatomic basis, and the acoustical branches comes because of the translational degrees of freedom. Okay. Now we can go to 3D. So you can already guess the result for 3D. In the case of 3D monoatomic crystal, you will have 3n branches. So you will have 3 acoustic branches and 0 optical branches, right? 3 acoustic and 0 optical, which is in 3D if you are dealing with a crystal having a basis of p atoms. So we are dealing with 3D, three-dimensional crystal. So in the 3D world, we are dealing with a crystal, insulating crystal, which has a p atoms basis, or p atoms per unit cell. So in this case, the number of k points is still going to be n, but the number of modes are going to be 3 times p times n. Out of this, the 3 modes are acoustical. So the number of acoustic modes is fixed to 3 now. It cannot exceed 3. And rest of the modes are optical modes. And how many are those? Those are 3 Pn minus 3. So these many optical modes. And of course, once again, the dispersion is going to be even more difficult to draw, because in this case, every k point has some omega value, and k points are over the 3D space. So in these cases also you draw dispersion along spatial directions. Okay, so you would draw, let's say, dispersion along the kx. So the dispersion drawn along the kx, and here is the zone boundary. So the zone, everything else remains the same. In this case, the zone will extend from minus pi by ax to plus pi by ax, minus pi by ay to plus pi by ay, minus pi by az to plus pi by az. So you will have these 3 acoustic branches, and then you will have a lots of optical branches. I'm drawing only 3. You can draw, and of course you have to have a mirror image of it here in the negative half of the build one zone, right? So I hope you will remember this. Total number of modes in a 3D solid is 3n. So we'll keep this picture. Now the question of why we are specifically looking at insulating crystals. So for that, we have to first understand what specific heat is. So take a material, you know the definition of specific heat. The amount of heat required to increase the temperature by 1 degree centigrade is the specific heat, right? I mean, it will be specific when you say amount of heat required per kilogram, then you are basically talking about specific heat for a kilogram of that material. Or you can talk about volume specific heat, which is specific heat per unit volume. Or you can talk about molar specific heat, which is specific heat per mole of material. Right? The units will change. In the first case, it will be joule per kg, in the per kg per Kelvin. In the second case, it will be joule per meter cube per Kelvin. In the third case, it will be joule per mole per Kelvin. Right? So now, when you are performing this experiment, imagine you are in a lab and you want to measure the specific heat of a solid. Okay? What would you do? If I am in your place, what I will do is, I will embed an heater in this. Heater of known power. I know what is the power of this heater. I may glue it, stick it very nicely so that they have a good thermal contact. It has a good thermal contact with the sample. And I will also put a thermocouple here to read the temperature. And the sample should be small enough to come to thermal equilibrium over, so you have to have the thermal equilibrium over the entire sample mass, right? So you can even think of having two heaters connected in series so that you are uniformly heating it, not heating it from just one side. Right? But these are practical aspects. But the other thing that you have to take care of, which is very important, is that you have to insulate it. This heat that you are providing to the sample should go only to the sample and should only be used up in increasing its temperature, because if the part of this heat is lost, then you are making an error in the experimental determination of the specific heat, because you would say, I have given an amount delta Q, the temperature has risen by an amount delta T, so therefore the specific heat should be delta Q by delta T, but you are forgetting that the delta Q that you gave, half of that was lost to the atmosphere. So, you are making an error of huge error, actually 100% error, right. So, you have to be careful. What you have to do is you have to insulate it completely from the environment, atmosphere. Now, how would you do that in a lab is something that you will probably learn in the experimental physics course, right. You have to evacuate, you have to put it in a chamber, you have to evacuate it. So, that will take away what kind of heat losses? The heat losses due to the medium, the gas which is present here. The gas acts like a medium that allows heat to be carried from here to here via convection, right. So, the convection losses are gone. Then you can have radiative losses, right. So, you have to take care of the radiative losses also. So, to take care of the radiative losses, what is typically done is you mirror polish the surfaces inside so that the heat is reflected back. Okay. Or what the other trick that people normally play is that the enclosure also is maintained at the same temperature T as the temperature of the sample, so that the temperature difference between the sample and the enclosure is 0, and therefore, there will be no cooling, there will be no radiative loss, right. So, you have to use all sorts of tricks, and that is what experimental physics is about, to measure the specific heat, specifically when you are away from the room temperature, either in the high temperature region or in the low temperature region, because then the temperature differential is huge, and therefore, the heat has a very high urge to flow into the colder regions, right. So, even by doing this, some losses occur. So, when you actually measure the specific heat, you take these losses also into account. So, there are ways of doing it. If you are interested, I can tell you about it in an extra class. Okay. So, you basically plot the temperature of this block as a function of time, and you see how fast it is losing heat, and that gives you an idea about the heat losses that you that are taking place. But you have to minimize them, and even after that there will be some heat losses. You have to take those heat losses into account and give a correct account of how much heat from the heat that you have provided is actually taken by the sample, and then measurement of temperature is not a problem as long as your temperature sensor is in good thermal contact with the sample. You will read the temperature all the time, right? You can read the temperature at any instant. So, you would see how the temperature of your sample is changing. So, you have given an amount because the heater power is known. So, you know how much heat you have given, and once you know that, then you say that the specific heat is del Q prime. I am writing Q prime. Q prime is the actual heat which you have given, right? Maybe the heater has given a heat delta Q, but a part of it is lost, which is delta Q double prime. So, delta Q by delta T, it is as simple as this. This is the I mean, in specific heat there is nothing else. As long as you can account for the heat losses, the measurement of specific heat is not a problem, but accounting for heat losses is one of the major issues. First of all, preventing heat losses, and secondly accounting for them, whatever residual heat losses are happening despite taking all the precautions. So, that is about specific heat. Now, a nice thing about specific heat is that it is an additive quantity, which means that in your system, why the temperature of your system is increasing, why is it getting heated up? It is getting heated up because in this material, in this mass, you have atoms, and these atoms are held together by spring like forces, right. So, when you heat it up, what is happening? Now, you have learned the lattice waves. So, you excite the phonons, you create more and more phonons. I mean, now I am talking in the language of phonons, but you can also try to understand it in a more classical language, where you say that the lattice vibrates more and more vigorously as you increase the temperature. But besides that, if you also have electronic degrees of freedom, if you also have electrons in the material, then the electrons will also absorb heat. The temperature of the electronic bath will also increase. So, the electronic subsystem will also participate in the specific heat. So, you will have a portion of this delta Q prime will go to excite the lattice, a portion of this delta Q prime will go into heating up the, I mean, I am using a very loose language, heating up the electrons in the material. And if the material is also magnetic, then you have magnetic degrees of freedom. You have spins ordered, you have spin waves, you are exciting those waves. So, a part of heat will go into that also, right. So, this is number 3, and on top of it anything else which is there, right. So, you take, so delta Q prime 1 or L, which is for the lattice, delta Q prime E, which is for the electrons, delta Q prime M, which is for the magnetic system, if it is a magnetic system. And you can also have, for example, let us say a phase transition is happening. You know what happens during the phase transition? The system absorbs heat, and if it is a first order phase transition, that is the latent heat. So, it is absorbing heat without changing its temperature, that is the latent heat. So, you can also have that, then the specific heat will manifest a huge jump, a huge spike, right. So, you have all sorts of things. So, in order to avoid all these complications at this moment in time, what we are saying is that my crystal is the simplest of all. It is an insulating crystal without any other degree of freedom, without any other channel, if you like the word channel, without any other channel for taking heat. So, this channel is not there, this channel is not there, there is no phase transition happening, but all the heat that you are providing is going into exciting the lattice waves, into making them vibrate more and more vigorously. Okay? So, that is why we have chosen this insulating crystal. So, now I know the heat which I give goes only here, and this is something that we have already learnt now. We know that the energy of an insulating crystal which I'm using this symbol U for it. So how much would be the energy? The energy of an insulating crystal, the energy by virtue of vibrations, lattice vibrations. Absolutely right. So this is summation over all the modes. So if you have 3pn modes, you have to sum over all the 3pn modes. Each mode is a quantum harmonic oscillator, which has an energy n plus half h bar omega. So you take the first mode, second mode, third mode, fourth mode, fifth mode, add up n plus half h bar omega. So we need an index here for the mode, right? And this can get very messy because now we have a k, and for that k, for any value of k, your mode could be this one, or your mode could be this one, or your mode could be this one, right? So we need more than one symbol, right? So we have k, then we can also put a little s over here. We can do a lot of, we can confuse ourselves with this nomenclature. So let's keep life simpler. Let's remember, so I'm going to just put a curly, well, that will also make life difficult. So I'll just put a little k here. K is this k, okay? So if it is 1D lattice, then all the modes are taken into account just by counting on k. But if it is more than a 1D lattice, then you know that you have to multiply it with a prefactor, and that prefactor will be decided by which crystal you are dealing with, right? So I will just keep it k, but remember that it's not just k, but k comma s, where s refers to s is the index for the mode. Acoustic 1, acoustic 2, acoustic 3, optical 1, optical 2, and so on. Plus 1/2 h bar omega k. Maybe last time I used the symbol little s here, and if ever I will write a book, I will not make that mistake. In every chapter, the symbols will be consistent. So this is U. Now from U, you go to the specific heat. So the point, the argument that we have made now is that this delta Q lattice, where will it go? It will go only in increasing the internal energy, increasing the vibrational energy of the solid, because it has no other degrees of freedom. It cannot take heat, it cannot do anything to that heat. It can increase its temperature by having more and more phonons, by exciting more phonons, by exciting these modes to higher levels. So therefore, delta QL will be equal to delta U. Do you agree with me or not on this? Amount of heat that you are providing is getting used up in increasing the internal energy, right? So therefore, if I have to write C, specific heat, there will be delta Q by delta T, and that will be delta U by delta T, because delta Q is equal to delta U. So that means if I can differentiate this expression with respect to time, I have solved the problem. I got the specific heat of an insulating crystal. So the specific heat, and I'm going to put a little v over here to designate specific heat at constant volume. But you know, for solids, the expansion is very small compared to gases, for instance, right? Because they are practically incompressible. So Cv is same as Cp, right? So, but I'm going to write Cv because that's how it is written in the books. You can just write C if you don't like this. In my notes it's V, so I'll just let it here. I'm going to send them to you. So it is del U by del T. That is it. Now if you are smart enough to differentiate this, you have solved the problem. But the problem is, where is the problem? Tell me. Is it easy or difficult to? Of course, it must be difficult. Otherwise, why would I take a pause? I will simply differentiate it and go home. right. So, you know what is Nk? Nk is the distribution function, right. Nk is given by 1 over exponential beta h bar omega subscript k minus 1. This function decides which mode is excited to what level, right. So, you have wave number k1, corresponding omega is omega 1, the corresponding simple quantum harmonic oscillator has energy eigenvalues n1 plus half h bar omega 1, right. And then what should be n1, that is decided by this factor. So, you will plug it in here and then do the temperature derivative. But the problem is that we do not know the exact functional form of omega k. Do we know the functional form of omega k? We know it for 1D lattice, that is mod sin k a by 2, right. But for more complex solids, we may not have. So, finding an analytical solution to this problem is difficult because we do not know, and also the number of modes are very large, is not it so? Number of modes are very large. So, therefore, this is a difficult problem. So, let me now give you a little more. So, I will just tell you a bit of history because otherwise the fun will be lost. So, let us look at the history of specific heat. So, very long time back, two French scientists, Dulong and Petit, they observed that the specific heat of, they observed meaning empirical observation. They did in the backyard of their home, they did lot of experiments and they were, they reached a conclusion, and the conclusion that they reached was that irrespective of which solid you take, as long as it is insulating, the specific heat always comes out to be a constant number, which is around 25 joules per mole Kelvin. Okay? And in fact, if you take metals also, it will be a little bit above, more than that, not too much, and I will explain that to you when we will go to metals, which is a long way from here. So, let us not get into that. So, the specific heat near room temperature for most of the solids that they examined turned out to be close to 25 joules per mole Kelvin. Okay. So, they said that this is the specific heat, this is how the specific heat of solid should be. This is much before we learnt about the structure of solids, that they are a periodic array of atoms and this and that, much before that. So, they said that the specific heat C molar specific heat should always be 25, close to 25 joules per mole Kelvin. This is known as the law of Dulong and Petit, Dulong-Petit law. And 25 J is not a coincidence, it is actually 3R, where R is the universal gas constant, which is 8.314. If you multiply it, you will get a number close to 25. So, it is 3R joule mole inverse Kelvin inverse, and they argued, or people after them, they argued that look, in a gas, in an inert gas, if you take the molecules of an inert gas, there are 3 degrees of freedom. Each molecule has 3 degrees of freedom. We are thinking of a molecule as a tiny bead, spherical bead. We are not talking about its internal structure. So, how many degrees of freedom it has? 3. And if you use equipartition of energy, then each degrees of freedom has half kBT energy associated to it. So, it will be 3 by 2 kBT, right. And if you take the derivative of that, you will get the specific heat at constant volume for a gas, right, and that will come out to be 3 by 2 R. But in a solid, because you have these atoms connected via springs, right. So, besides the translational degrees of freedom, you have vibrational degrees of freedom also. So, you say that you have 3 translational, 3 vibrational. So, altogether 6 degrees of freedom. So, therefore, the specific heat should be 6 times half kBT. That should be the internal energy U, and then you take the temperature derivative of it. So, you will get how much? I said half 6 kBT, that is U, and then if you take del U del T, then what you get is the specific heat, and that turns out to be 3 R. That is the way they justified it, and people believe that this looks very sound, this should be fine. But the surprise came when the experimentalists, they started doing such measurements at low temperatures. When they measured specific heat at low temperature, a big surprise came. What they discovered was that the specific heat near room temperature is indeed close to 25 joules per mole Kelvin, which was determined by Dulong and Petit using very crude methods, experimental methods, but because of the experimental rigor, working very hard day and night in the backyard of their home, they arrived at this result. But more refined experiments showed that yes, indeed, this is 3 R, close to room temperature. But once you start cooling your sample down to lower temperatures, then things get messier. So, if I plot C as a function of temperature, which is one of the classic experiments that you do, measure the specific heat of a solid as a function of temperature, right. So, what you would see is that it is indeed close to the limit given by the two French scientists, 3 R. But as you start cooling down the sample, it starts dropping, drops, 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 and goes to 0. Well, this was puzzling. Why is the specific heat temperature? I mean, if you don't know this, what all that we did, all that we know that the temperature dependence is coming here. But if you don't know this, then this is very surprising. Now you know the temperature dependence is coming because of this factor, because of the Bose factor. But at that time, the Bose statistics was not known. So, to explain this behavior of specific heat, we are going to use two models which you may have already heard about, have come across these models. The first model is by Einstein, none other than Albert Einstein. Now, you may say, I know Albert Einstein only for his work on photoelectric effect, and maybe later he worked, not maybe most people just know that he did general theory of relativity, he wrote GTR, and they feel very really what to say, they say that, oh, Einstein's the name, when you name Einstein, MC square is what comes to mind. But Einstein did a lot of work on various problems, various challenging problems at that time, right. His work on diffusion, right, that is, I mean, that is and photoelectric effect, and then of course the specific heat. So, Einstein jumped on this problem. So, he gave a model of solids. Condensed matter physics is all about models. What do? You try to model a real system. You look at the behavior of real system in the lab, and then you say, oh, let me try to explain this behavior. To explain this behavior, let me model this system. Okay, so let me now write the Hamiltonian, and let me now start solving it. This is what you do. So, he gave a model And in fact, his model did reproduce this result to a great extent. Specific heat indeed came down. I mean, after all, it's Einstein. He touched on the, I mean, he said, I'll look at it. He thought about it. He came up with a model. He cooked up a model actually. And what that model is, we will talk about that in the next lecture. Let's not worry about that part as yet. But his model really explained this departure from the Dulong and Petit law. Not only explained the departure, but in fact, whatever experimental data was available at that time, Einstein model was very close to that experimental data down to very low temperatures, but at very low temperatures, his model failed. So what is happening at very low temperature, I didn't tell you. So when you go to low temperature range, by low temperature I mean, let's say for a typical solid, low temperature is below 10 Kelvin or 20 Kelvin. So at such low temperatures, a very remarkable thing happens, something as remarkable as this, that every solid is 3R, independent of whether it has carbon in it or it has gold in it, doesn't matter. For as long as you express it as per mole, 1 mole of every solid will have this much specific heat, 3R. Right? Low temperature is equally striking. And credit goes to experimentalists. They measured one sample after another, and they analyzed the behavior of these samples at low temperatures, and they found in every case, without fail, the specific heat at low temperatures goes as T cube. C is proportional to T cube, whether you are measuring diamond or you are measuring a sodium chloride or you are measuring aluminum oxide or silicon oxide, doesn't matter. The specific heat at low temperature is T cube. And Einstein's model could not explain this. Shall I call it universal? Why not? I mean, it is universal. Irrespective of which solid you take, and experimentally proved. I mean, in fact, it came from the experiments first. That is why people said, oh, what is this? The model doesn't work at low temperatures. And then came the second guy, Debye. Then came Debye, who was also, one of the top scientists at that time. And Debye, he gave another model, which we are going to discuss maybe in the third lecture from now. And he got it. He got not only the 3R, but also the T cube, and also for a good part in the intermediate region, he got his calculated specific heat very close to the experimental values. Okay. So these are the two models that we are going to study. But now, in fact, what we have done is we came far ahead of both Einstein and Debye. We directly wrote this expression in terms of phonons. And if you can calculate this derivative, you can actually get the specific heat. So what I am going to do is, I am going to discuss Einstein and Debye in next lecture, but in today's lecture and in another 10 minutes or so, what I am going to do is, I will start from here and show that both these results can be obtained without using any model, any of these models. Okay? So let's try to do that. So first, let's do the easier part, which is when you are in the high temperature side. Okay? So when the temperature is high, so Nk is 1 over exponential beta h bar omega k minus 1. So, if the temperature is too high, that means kBT is much greater than h bar omega k. What does it mean? For all omega k's, what does it mean? It means that your temperature is so high that you have excited all the modes. You have excited all the modes, right? You can write this as 1 by beta. Beta will go here. So, essentially what you got is, or beta h bar omega k is much smaller than 1, right? Now, what happens to e to the power x when x is very small? You terminate the series at 1 plus x, isn't it so? You do that. So, since your x is, now here x is this number. So, since this is a very small number, beta h bar omega k is a very small number because the temperature is too high. Therefore, you can write your n of k as essentially 1 by 1 plus x minus 1. So, 1 plus beta h bar omega sub k minus 1. So, 1 and 1 got cancelled. So, remain with kBT divided by h bar omega k, right. So, that plug this in here in your expression for u. So, what you will get for u? So, your u will be summation over all the modes, and then this will be this quantity kBT, right, kBT plus h bar omega k plus 1/2, and then you have h bar omega k, right. That is your u, and you can rearrange it. You start taking the derivative. So, you take derivative del u del t. What you get is this term will be 0, derivative of this will be 0. Here the temperature dependence is now h bar omega k will get cancelled from h bar omega k in the second term. So, what you are left with is just kb, right, of summation over all the modes. And let's say we are dealing with monoatomic 3D crystal. So, how many modes are there? 3n. Only 3 acoustical modes are there. Just for simplicity, I mean, you can write 3pn here. You can as well write 3pn. So, this is nothing but 3pn, you can write that way, or 3n kb. And if you are solid, so this is your C of V, and if your solid has 1 mole of atoms, then n can be replaced by Avogadro's number n sub a times kb is r. So, therefore, you got the result already that Cv for 1 mole of any solid would be 3r at high temperatures, right. So, we can stop here. Thanks.